So this study is devoted to the out-of-plane behavior of masonry walls reinforced by composite materials. My name is REBOUL, and this work has been conducted in collaboration with LARBI, Emmanuel FERRIER, and Karim Koucha. We question here the effectiveness of TRC or FRCM composite to strengthen hollow concrete blocks masonry structures in the context of seismic solicitation. We think that TRC is a promising alternative to FRP retrofitting solutions because the characteristic of the substrates are more in adequation with, are more appropriate with the characteristic of the reinforcing material. In previous studies, we have investigated the in-plane response of masonry walls reinforced by TRC materials, and it appears that though the analysis has been conducted under both static and cyclic loading, and it appears that TRC are effective in increasing the lateral strength of masonry walls. And it appears that the reinforced wall have a good ductility and a good energy dissipation, because the cracking behavior of TRC provides an additional dissipative mechanism which compared to FRP, which can be interesting at the ultimate state. And as the experimental results were conclusive under in-plane solicitation, we have decided to continue with the study under out-of-plane solicitation. And with this in mind, we have designed the following test setup. In fact, all the edges of the masonry walls are contained in steel channels, and these steel channels are in turn restrained from moving laterally. And along the base of the wall, we have steel profiles which come into contact and that are connected to the strong floor thanks to steel rods. Then lateral vertical support is provided by connecting the steel channels to a reaction wall, which is here. Concerning the load, the test protocol follows the different steps. Firstly, a vertical axial load is applied, and thanks to a hydraulic actuator, and it is kept constant during the test, thanks to force control of the hydraulic actuator. Then, as regards the out-of-plane loads, they are applied thanks to an airbag, which is which is located between the masonry walls and the reaction wall. The tests are conducted under monotonic static tests. The airbag is at the center of the wall, and it covers around 13% of the wall area. All the walls are 2 meters long and 2.2 meters tall, and they are built with hollow concrete blocks whose hollow concrete block units, whose thickness is around 150 millimeters. They are assembled with a common mortar, which is composed of ready-for-use mixed and common cement. Concerning the reinforcement, we have decided to work with two types of reinforcement. The first material is a fiber reinforced polymer with flax fabric, and the second one is a textile reinforced concrete with glass fabrics. In fact, to choose the number of fabric layers has been chosen in order to have the same tensile load, and it has been checked by performing direct tensile tests on composite samples which have been realized when the walls have been reinforced. And we can see that FRP with one fabric layer and TRC with two fabric layers give the same tensile load, that is about 8,000 decanewton if we take a width of 10 centimeters. It is important to note that the thicknesses of the composites are really different, because TRC are 3 or 4 times as thick as FRP. 3 reinforced walls have been tested, and for all the configurations, only the tensile face has been reinforced. And in the first configuration, which is denoted squared configuration, 3 100 millimeter bands with a clear spacing of about 60 centimeters have been used in the horizontal direction, and 2 100 millimeter bands with a clear spacing of about 75 centimeters have been used in the vertical direction. The same configuration has been adopted for TRC and for FRP. Then, concerning the TRC, we have added a diamond-shaped configuration where composite bands have been located transversally to the potential that the failure line that we could expect with our boundary conditions. In fact, the unreinforced wall has not been tested until failure. We have stopped the test when we have achieved the post-peak zone, and we have decided to repair it after with the squared configuration and with the TRC material. To prevent a potential uncoupling between masonry and textile and strengthening bands, an anchorage has been created at the ends of each strengthening bands, and in fact this anchor consists of unidirectional carbon mesh which are embedded in chemical routing products in order to provide a secure anchoring point. We have decided to introduce the sleeves until the intermediate, the second vertical surface of the blocks. To monitor the response of the walls, we have 1 laser sensor and 5 displacement transducers. The laser sensor provides information on the displacement at the center of the wall, and the 3 other displacement transducers give the displacements of 3 points around over the surface. Then the additional 2 displacement transducers give information about boundary conditions. One is located along the base of the channel section on the base, and the other one is located on the channel section, on the vertical channel section. It appeared that in our test there is no slip, so the test setup prevents the wall from slipping, but we have little displacements on the vertical channel section. So to compare the wall between them, I have decided to work with the relative displacements between the center of the wall and the lateral channel section. As regards the force, a force transducer is associated with the hydraulic actuator to control the vertical axial load. And as regards the out-of-plane load, we have a pressure sensor that records the pressure in the airbag. And we have added the force transducers which give the load which is transmitted to the reaction wall. So the results for the unreinforced wall are as follows. In fact, we have here the equivalent out-of-plane load given by the force transducers and the out-of-plane displacement at the center of the wall directly given by the laser sensor. And we can see that we have a first inner zone where the wall integrity is preserved. Then we have a vertical crack which appears and which marks the beginning of the nonlinear zone. In fact, it is important to note that the vertical crack progresses through both vertical joints and blocks, and this will be the case for all the tested walls. In fact, all the blocks the failures are not concentrated in the joints in our case. Then later in the loading, we have inclined cracks that are formed, and 2 are directed along the lower corners, and on the upper sides we have inclined cracks but with a lower inclination. In fact, the failure mode is symmetrical, which can be a good thing for our setup. Once the cracks appear, their opening increases as the load with the displacement with the load. Concerning the wall reinforced with FRP, we can see that the first phase is larger than in the previous case. So the FRP delays the first macroscopic damage, and we can say that the crack pattern is rather similar to the previous one. In fact, we have a vertical crack, which is have a slight deflection here, and we have inclined cracks which are directed toward the corners. And it seems that FRP do not deviate the cracks that are formed. They only contain the cracks and control their opening. We can see that in that case we have a failure of at the central horizontal band of the FRP, and if we look at a strange gauze which is glued there, we can see that we reach 8,050 microstrands. That is to say, we are at 90% of the ultimate tensile strength. So I think that there is a problem, or that shows that the stress redistribution are not really optimized with such a material, and it shows that our anchorage systems may be efficient in the present case. And we can see that we have an increase in the maximum load, and we have a good ductility. Concerning the square GTRC walls, we have the same crack patterns, and but we haven't got any failure about the GRC materials. And the first linear face is not as large as in the case of FRP, but the real difference is in the post-peak zone, where we have a load loss which is really gradual compared to the previous one. For the repaired wall, we can see that we have the vertical line, the crack, the previous crack pattern, and we have more inclined cracks that appear, but we have the same maximum load than in the reinforced wall. That is to say, we have the same efficiency for the repaired wall that for the reinforced one. And in that case, we have only some delamination, debondings, where the cracks are a very large opening. And in the later case, for the diamond GTRC wall, we can see that we show that the first vertical cracking around 2000 decanewton appear firstly as in the unreinforced wall, and then we have inclined cracks that are contained again by the TRC materials. And we can see that the maximum load is the same as for the other configuration, the other reinforced configuration. If we compare all the walls, we can see that the reinforced or the repaired configurations enable an increase in the lateral strength, and the gain is about 20 to 30%. And we also can see that no wall experience, no configuration experience sudden drop in the load when they reach their maximum, and they all present some ductility and some displacement capacity after having passed the maximum load. And if we compare in terms of loads and in terms of displacements, we have seen that all the repaired and reinforced wall load have about around the same maximum load, but it is interesting to note that FRP1 has a greater load. The FRP unable to delay the first damage, the first microscopic damage. And if we look at the displacements and if we compare the wall with the ductility coefficient, we can see that TRC enable an increase in this coefficient better than the FRP one. To conclude, I would like to say that we have shown that the reinforcements that we have used, regardless of the nature and the adopted configuration, lead to higher out-of-plane capacity. And we have shown that TRC was an effective way to strengthen masonry, but also to repair masonry structures. And we have with TRC and FRP the same maximum load, but FRP unable to delay the macroscopic damage. And we have an advantage with TRC in our case because TRC reinforcements lead to higher ductility than FRP reinforcements. And about the failure mode, we can remind that cracks are not deviated by the strengthening bonds, and it appears that stress redistributions differs depending on the reinforcement materials, because in the case of flax FRP, we have a failure on the central horizontal band, but in the case of GTRC, we have only micro cracks on the outer face of the bands, so we have an interaction between the substrate and the materials, which is different depending on the case. Thank you very much.
Thank you.